Hello, everyone. Welcome back. Hopefully you can hear me. Cool. Thank you. Excellent. Okay. Happy New Year. Welcome back. This is CSCE 317. I'm your instructor, Jason Bakos. We'll start out by reviewing the course syllabus, which hopefully you can see up on your screen. The catalog description is shown there at the top. It's a bit out of date, but it still captures the main concepts that we'll cover in this course. This course focuses on the design of computer systems, and we'll mainly focus on two concepts in particular: how components in a computer system are connected, or how interfacing works between computer components, and how to evaluate system performance. So last spring, I think I mentioned this in my email. Last spring, we were in the process of redesigning this course to take advantage of the brand new lab that was built in SWIR Engine 3D22. It was built specifically for this course, but we were never actually able to use the lab before the university closed down. And so we're now redeveloping this course again to support virtual instruction. So what this means for you is that you shouldn't expect this to be a polished course. This is essentially the first time we've taught it in this form. As I also mentioned in the email that I sent over the weekend that you hopefully received, we have two sections. Most of you registered for section 001. It's set up with an asynchronous lecture, but we created section 2 over the break with a synchronous lecture, and this was in response to a feedback bloodbath that I received as a result of running my other course from last semester asynchronously. So I taught CSCE 611 asynchronously and in the fall, and it didn't work out very well. Students were very unhappy with that. So we're trying something different here. If you're registered for section 1, you should be able to attend the synchronous lectures of section 2. And if you're hearing this live, obviously you've already figured that out. But this should be recording, and the lectures will be available offline asynchronously as well. And I haven't tested that yet, but in theory, the recordings should be available on Blackboard somewhere, probably under Collaborate. You guys probably know more about this than I do, because this is the first time I've used Blackboard Collaborate. Last semester I used a different platform. Now, I'm aware that the idea of having to click through a special section to get to the live lecture is janky and awkward, and I apologize for this. But again, this is a result of a last-minute change. So just to clarify, we'll be using Blackboard for the live and the recorded lectures, and I'm using Moodle, which is the dropbox.csc.sc.edu, to provide handouts to you and to allow you to submit assignments and see your grades, and also to communicate on the forum. So basically, I'm using Blackboard only for the lectures and Moodle for everything else. And this is just because I like Moodle better. I'm more accustomed to Moodle. Although if we continue to run the course like this, I'll try to consolidate everything onto one site. So again, it's a little janky, but so bear with me. The textbook for this class is shown here. There's a picture of the cover shown on the syllabus. It's the Embedded System Interfacing by Marilyn Wolfe. The textbook, though, doesn't cover all of the topics that we plan to cover in class. So we'll be providing additional materials through Moodle. Mostly it'll be in the form of lecture slides, which you can download. But we'll probably also have some actual documents, some manuscripts, because The materials that we're developing for this course will form the basis of a new textbook that I'm writing with the TAs Charles and Philip. So all of this material will be available on Moodle, and the textbook here is just a reference. We've modified the course learning outcomes for this semester, again, as we refine the way that we teach this course virtually. Our plan is to cover low power system level interface protocols, which is basically all we covered last spring because things got so screwed up. But this version of the course will be more conceptual and less applied, and this will give us more time to add coverage for new topics beyond the interfacing material. So we plan to cover real-time scheduling and control theory, queuing theory, and a few topics that overlap somewhat with stuff that I normally cover in 6.11 and what I used to cover in 6.13 VLSI, which is hardware description language, high-level synthesis, and device theory and signal integrity concepts. So this will give me an opportunity to resurrect some old stuff that I have from when I taught VLSI design, and also to cover things from 6.11 a little bit more thoroughly, some of the lower level stuff. Now you might be thinking, well, geez, these concepts are fairly broad. These are kind of all over the map, but they are linked thematically in the sense that they're all important concepts related to the design of low power purpose-built computer systems, which these days are known as Internet of Things systems and cyber-physical systems. Those are what they're called now. Those are kind of, you know, buzzwords, but that's really what we're talking about in this course, is Internet of Things and cyber-physical systems. I've got some important dates listed here in section 6. The schedule this semester is unique because we have no spring break. So there's these kind of, I guess, randomly distributed days that classes are canceled. I think they're called wellness days. I think the only one, though, that intersects our lecture is the one on Wednesday, April 21st. So that won't affect us till the end of the semester. But I've got all the important dates I could think of there. We've got the, of course, next Monday's class is canceled, as it always is in spring. The last day to drop without a W grade is, you know, basically a week from now. We've got a cancellation on February 15th, and I even put the last day to apply for May graduation, just in case any of you are graduating. And withdrawal date is March 27th, which is, you know, kind of a month before the semester ends. And last day of class is the 26th, and the final exam is scheduled for April 30th, assuming that I read that correctly from the final exam schedule. So those are useful to have access to. This syllabus, by the way, is linked on Moodle. You can get to it. Let's see. Section 7 has contact information for myself and the two TAs, Charles Daniels and Philip Conrad. Neither one of the TAs comes to campus, but they're available for video conference by appointment. And unlike last semester, I too will probably not be on campus, which is, if you know me, that's unusual for me, but that's due to the university has a new COVID testing requirement, and I'm afraid of, you know, if I get tested and it comes up positive, I'll risk, you know, my kids being barred from school. I've got school-age kids. My kids might not be able to go to school. So I don't want to risk that. So I'll probably just be working remotely all semester, but I'm more than happy to meet any of you virtually almost any time. So please don't hesitate to contact me to schedule a meeting. I got no problem with that. We'll have, moving on to section 8 here, grading structure. We'll have 3 exams, several quizzes. I don't know exactly how many quizzes we'll have. And we'll have a few small projects. I don't know how many of those we'll have. We're still deciding on the number of projects because we're trying to be extra careful with this aspect of the course, because we had a lot of problems with projects last semester. So generally, my courses are usually very applied and are very focused on projects. And for the past 22 years of me doing this, that's worked out really well, and the students enjoy that. But I haven't quite figured out how to do projects in a virtual course. It's difficult because my projects, have always been team-based projects. So you have a partner, and so you can bounce ideas off each other, and you're in the lab and can ask questions. So when you're kind of working in isolation, it's difficult to do a complex, large-scale project. And I tried to do that last semester, kind of like I always have in the past, and it was a disaster, to put it mildly. So this semester we're going to do. We'll have some projects, but they'll be limited in scope. But the exams, we expect the exam 1 will be the week of February 22nd. Exam 2 will be the week of March 5th, and the final, as I mentioned, is set for April 30th. And the weights of each of these is listed there in section 8 on the syllabus. If you have any documented disability, please contact the Office of Student Disability Services, and they can arrange for appropriate accommodations. Typically, this is, like extra time on the exams and that kind of stuff. And I obviously, please, don't hesitate to contact them if you need to. Section 10 is the syllabus change policy. As I mentioned, this is not going to be a super polished course. We're trying to adapt to the times, and so we may end up changing things around, in particular the topics that we cover. I don't really have a good sense of how long I'm going to need to spend on each of these topics, so even though I have a good idea of what I want to cover, I'm not sure about the time required. So, but we'll give you plenty of notice if we make any changes. Section 11 has the electronic resources, and as I mentioned, and I'll say it again, even though this might seem repetitive, but we'll be using Blackboard for the live and recorded lectures. Moodle is for everything else, so we'll have all our downloads on there and such. Yes, section 12 is the grading scale. We use the standard grading scale, 90, 85, 80, 75, 70 grading scale. I think this has become pretty standard lately. Section 13 is the academic honesty policy, and it states that any honor code violation will result in a grade of 0 for the associated assignment, exam, or quiz, and a report to the relevant university office. The primary type of honor code violation for this type of course that we're worried about is collaborating on the quizzes and exams. The quizzes and exams will be administered via Moodle, and they are open book and open internet. So you can use whatever resources you want while you're taking them. Of course, the exam difficulty will be adjusted to be consistent with that. So these will be more difficult than if they were not open book, open internet. But the only thing we're worried about there is that we want you to work alone on those. Okay, so section 14 describes the rules for project submissions. These are important rules because they tend to come up quite often during the semester. And as you might imagine from reading these, each of these rules were born out of a specific issue that we've had in the past. So, but basically, to summarize, each submission that you submit must compile to receive credit. So, we try to give partial credit, obviously, and we spend a lot of time developing rubrics, grading criteria, specific things that we look for in your code to give you partial credit if it doesn't work perfectly. But if it doesn't compile, then that just kind of indicates that that you didn't even make it compile. So we don't give credit for things that don't compile. The due date is the due time, I should say, is 11:59 p.m. on the due date. So 1 minute before midnight, because midnight is technically the next day. Late penalty is 5% per school day, and it's capped at 30. So this is a very lax late penalty. We want you to do all the projects. We don't want you to kind of give up. So we're not penalizing you very much for having late. And also, we don't want you to submit something that doesn't work at all, when if only you had a little bit more time, you could have got it to work. So basically, we want you to feel that you can submit things late if needed. Only one submission. Oh, by the way, when I say per school day, that doesn't include weekdays or weekends and holidays. Only one submission is allowed, because, and this is really a consequence of the late penalty. So some students kind of game the system a little bit, where they submitted on time, but then they figured that that if they could also resubmit it late and might get a higher score than the initial submission that was on time, and that kind of stuff, and which is fine, except that tends to create so much grading workload that it's not very fair to the TA. So only one submission is allowed. The final project due date is reading day, which is the day between the end of classes and final exam week. And then also, any grade issues that you have need to be raised. The original version of the syllabus said resolved, but I just changed it today to raised within 1 week of the release of the grade, meaning that if you have a question about your grade for a project, let us know within a week of us handing them back. And then there's the last bullet here is some aspects of the project score will involve the organization and formatting of your code, but I mean, we're not going to be super anal about this, but we're hoping that we can encourage you to write well-structured code. So that's it for the syllabus. Let's see here. I'm going to try to switch over. Let's see. Sorry. I'm going to try to share my whole screen now. Okay. So hopefully you can see that. Okay, so this is what Moodle Dropbox currently looks like. It's pretty empty here right now, but we do have the syllabus. You can download that, and the lecture 1 slides. I'm not sure if I'll get through all those slides today, but those are available. And then we have an announcements forum. Anything that's posted on announcements is also broadcast to everyone in the class. So you'll get an email with everything that's in the announcements forum, and then I'll be adding additional forums that we can use for discussion. Those actually worked out pretty well last semester. That was one part of last semester that was nice. Okay. Switch over now to my slides. Okay, so before we dive into any material, I'd like to briefly introduce the course. I always like to do this before all my classes, basically tell you why you're taking this course, why are you spending your time and money on this course, why is this important and relevant, and how the material we're covering will benefit you in your career. Because I think that's important, that you should know, why we're doing this. This course, as I mentioned, is about embedded and cyber-physical systems. Embedded systems are computers that are designed for a specific purpose. So embedded systems have a very specific and very limited functionality. And also they need to meet certain requirements, but they have to have minimal cost. So I mean, on the other hand, when the term processor, computer processor, or CPU is used without the embedded qualifier, the embedded designator, so if you just say processor, it's generally assumed that you're talking about a laptop, desktop, or server processor. But these days, the distinction between an embedded and a laptop processor is beginning to blur, as you might know, because you can buy laptops now with ARM processors, which were traditionally considered embedded processors, right? But those processors, the high-end ARM processors, are high-end embedded processors, high-performance embedded processors, and their level of performance and their power consumption is really approaching that of laptop processors, which is why you can use them to power a laptop. And in fact, ARM processors were used years ago in servers, believe it or not. But in this course, our focus is on the low power embedded processors, the very lightweight processors. And so another key term that we refer to here is cyberphysical systems. I mentioned, that's kind of a buzzword now. And these are embedded systems that involve sensing, communication, and control, or well, actually they link sensing, communication, and control. And what that means is that they have a sensor and they do some computing on the sensed data, and then they use that to control something physical. And it's the control part that is what distinguishes cyberphysical systems from any other normal embedded systems. So I got some examples here on this slide, and if you look at these examples, the Tesla self-driving computer in the upper left-hand corner, see this thing here, is and the satellite, I got a picture of a satellite controller here too. Those are certainly cyberphysical systems, right? Because they're controlling something. The Wi-Fi speaker, smartwatch, Wi-Fi router, let's see, Google Glass, the weather station. Those are not cyberphysical systems because they have sensors, but they don't really control anything. Camera is a cyberphysical system since it controls the focus, shutter, and aperture. I mean, in response to light, right? Light sensor. And of course, the thermostat, right? That's a cyberphysical system. It controls an HVAC system, and a drone controller has flight control, so it's a cyberphysical system. So that's the kind of systems we're talking about. Now in this case, obviously the Tesla computer is by far the most powerful of all of these, but it still doesn't, it's still not in the same league as like a high-end desktop processor, right? Because it still has limitations on its power consumption. On the other hand, the smartwatches, the Google Glass, those are probably maybe the weather station. Those are kind of the low end of these embedded systems. Okay, so what kind of distinguishes this course and the stuff we're teaching in here from any other programming class is that the design of embedded and cyberphysical systems focus on design parameters, which are properties or attributes that define their performance and various aspects of their cost. In cost, meaning their power consumption or physical size, heat dissipation, that kind of stuff. And so there's the term constraint is when you place a minimum or maximum value on a certain parameter that has to be achieved. So you might have a power envelope constraint, which would be measured in terms of watts, or you may have a performance constraint, which could be operations per second, but it might also be like frames per second if it's like some sort of computer vision system or camera, or like a autonomous vehicle where you have to achieve a certain FPS, or maybe they measure it in pixels per second. But there's also constraints like interconnectivity, which is like the I/O speed might be a requirement, how fast you can get data in or off the chip, or it could be in latency, like how fast can I expect to get an answer after I send an input into a chip. So you may not care about the throughput, you may not care about the rate at which I can process requests, you may only care about the latency. So if I'm doing like a high-speed stock trading system, for instance, I don't, those systems don't care anything about throughput because, that's not the objective. The objective is to be able to make a trade decision as quickly as possible after receiving a price or the state of stocks or commodities or something like that. So that's a latency constraint. Now, on the other hand, you may also have optimization goals, which is a metric that needs to be maximized or minimized to become competitive. So, you might say, well, I've got a device here, it achieves all my constraints, but its battery lasts longer than the competitor, or, maybe it's a little bit more snappy than the competitor. And so that's not necessarily a constraint, but it's a goal. And then trade-offs come up all the time in embedded systems. This is, as you might imagine, this is where you have to decide whether to sacrifice one thing for something else. So I tried to show an example of that here. Now this is well, first of all, design constraints is like sorry, this is an example of these numbers are all approximate. That's what I'm trying to say. These are all illustrative. So don't assume that these are super accurate. This is just meant to be illustrative. But this is a spectrum where on the left side you have smaller power envelopes, and on the right side you have more performance. So this is kind of a trade-off between power and processing power, right? Electrical power and processing power. So on the left, we have a light-up greeting card, which is, believe it or not, is a computer. There's a computer in there, and it's designed obviously to run for a long time, maybe years on a small battery. So it's designed for that. So obviously its performance is not very high. But the crazy thing is that these cards generally use like Arduino style processors. Philip told me that. I didn't even know that. I was surprised to hear that they used an Atmel AT-Mega chip, some of them, which is crazy because when you think about it, that means that the processor inside of a greeting card is technically able to generate 4K deepfake video footage. I mean, in theory, because you could, cross compile, high-end code and run it on one of these things. But obviously it wouldn't be a good choice to run that kind of code because, you'd have to wait a long time for it to finish. Let's see, on the right side here of this figure, I'll go over on the right, the other extreme, we have the, as I mentioned, probably the most powerful embedded system ever deployed. I mean, frankly. And it's the one that controls the Tesla self-driving capability. But even that computer is limited to having a power consumption that has to be less than a high-end desktop PC, because when you think about it, right, if you build a high-end gaming PC, you're going to put a 1200 watt, maybe 1200 to 2000 watt power supply in there. You're talking about 1 to 2 kilowatts, right? Let's just assume 2 kilowatts. You have a monster machine, right? Well, the Tesla cars only have a 100 kilowatt hour battery, right? So that means that a high-end gaming PC would kill a Tesla car in, you know, like 50 hours of running, right? So, but those chips that they put in those cars are incredible. I mean, they're very, very specific to that task. They're all custom chips. They used to buy NVIDIA chips, the Jetson chipset, but they don't anymore. They roll their own silicon now. They're crazy. So that's interesting. So the number I showed there on the bottom is the watts, and then the number of instructions per second. And the number of instructions a CPU can execute per second depends on its clock frequency, the number of cores, and other features like superscalar execution, simultaneous multi-threading, speculative dynamic scheduling, all that kind of stuff. So there's a lot of, that's why we have this huge range of processors now, because there's a lot of ways to improve their performance, but it's going to cost you in power. But here's the caveat to that, and this I didn't realize this myself until recently, but low power computing technology is horribly energy inefficient. And you might say, wait a second, that doesn't make any sense. You're saying that a low power processor is energy inefficient? Yeah. The ATmega 328P, and this is the processor, by the way, that we targeted last time I taught this course, last spring. The plan was, when I taught this course last time, we were going to write a lot of code, and we were going to actually make hardware with these ATmega 328Ps, because the lab we have now in Swearingen, you know, we've got all the bench equipment and the soldering and all that stuff, and we were going to actually basically make a weather station. But prior to that, I hadn't really had a lot of experience with those chips, and so those chips use like 20 milliwatts of power, but I was surprised that its number crunching capability is limited to, you know, if we're doing floating point. Now you could argue that who's going to do floating point with one of these, but you know, we have to pick some benchmark, right? So the floating point capability of this Arduino chip is 200 kiloflops per second, and this makes it 180 times less power efficient than a Raspberry Pi. Because it uses 9,000 times less power than a Raspberry Pi, you know, basically at full load, right? But it's 136,000 times less performant. So it's 180 times less power efficient than a Raspberry Pi. Likewise, you know, if you compare a Raspberry Pi to a supercomputer, so the Summit supercomputer is was the most powerful computer in the world until recently. It's over at Oak Ridge National Lab. It has 2.5 million processor cores, believe it or not. Has 3 petabytes of RAM, and it has 200 petaflops, quadrillion flops per second, and it uses 10 megawatts of power, which means that it basically needs almost its own dedicated power plant to run the thing. So it uses, so the Raspberry Pi uses 700,000 times less power than Summit, but it's 7 million times less performant. So it's 10 times less power efficient than the supercomputer, which is strange. So the bigger the computer you build, the more power it uses, obviously. But it's also more efficient because because of the nature of computing technology. It's actually difficult to efficiently do computing at very small scales and at very low power. Now, these trade-offs, by the way, you might be thinking like, what are we talking about here? Are we talking about hardware design? Are we talking about software design? I mean, you teach hardware design courses, right? Yeah, but when I say embedded system, I'm really talking about system design, which includes both the hardware and the software together. So in this semester, we're planning to present these concepts in two parts. The first part of the course, I want to cover so-called bare metal programming, which is the art of programming without the benefit of having an operating system, which means that your code has to be written in a way that directly interacts with hardware. Or maybe not directly with hardware, maybe through a library called a hardware abstraction layer, but not an operating system. Now you might say, well, why is having an operating system so beneficial? Well, it provides services and it provides scheduling and load sharing, and it's kind of like a safety net. If you and when you write code on an operating system, which is what you've done in every other course you've taken at the university, you never have to interact with hardware. But when you write bare metal code, you do. So really what we're talking about here is how to do software-hardware interfacing. So we're going to cover concepts in this class such as interrupts, programmed I/O, pulse width modulation, which I might even get to those today. We're also going to cover common system level protocols. When I say system level, I mean, basically chip to chip protocols, or CPU to peripheral protocols. And that's really there's a lot of content there. There's a lot of stuff to talk about with that. So we'll spend some time on that. We're also going to cover concepts related to how constraints are determined for embedded and cyberphysical systems. So what I mean by that is when you have a constraint, I mentioned constraints are kind of like rules. They're goals that you have to achieve or nothing basically works. So what we're talking about is real-time systems here. It's not a thing where it's like, well, no, we want to speed up the game so you get more frames per second or higher resolution. No, this is something where generally with a cyberphysical system, you're trying to control some physical thing in real time, and so your performance constraints are hard. And so in order to really cover that, we have to cover a little control theory and real-time scheduling and queuing theory, which are the three things that sort of support this idea that you have this interaction with the physical world and constraints that result from that. And then the second part of this course will focus on hardware concepts. So I plan to cover some system Verilog. Now, if you've taken my previous course, CSCE, the course I taught in the previous semester, I should say, because these courses are not sequenced. If you took CSCE 611, I think most of you have not. I think most of you take this before 611. But if you did take 611, you're already familiar with System Verilog. And in fact, I think it's also covered a little bit also in 313, if you've taken that course. We're going to cover some more System Verilog. We're going to focus more on state machines in here than we did in the other courses. I also want to talk about high-level synthesis, which is when you generate hardware from software, because that is an emerging, that's a very new concept in embedded system design, and that's going to be big, I think, down the road. And then we'll also cover CMOS design, which is, we'll go down to the low level. We'll talk about transistor level design and CMOS and semiconductors. And the reason for that is because it's relevant when you're doing special purpose computing, not only to understand why your chip uses more power than another chip, but also it's useful to understand transmission lines and signal integrity. So why am I limited on how long wires can be between chips, and why do I have to worry about bit errors, and how fast can I run this interconnect, and that kind of stuff. So we're going to talk about that as well. Okay, so let's see. Right, so this kind of ties up the introduction here. So we want to talk about how hardware and software is customized. We'll talk about interfacing and trade-offs. So mostly this course will be conceptual, but as I mentioned, we'll have some hands-on stuff. We'll have some simple projects. Hopefully that will be a little bit more manageable in this format. Okay, so let's go ahead and we have some time left. So I'm going to go ahead and just jump straight into some content for you. I'll probably review this stuff a little bit next lecture, just in case there were some students that didn't see this live. Or but so let's first talk about how software communicates with hardware. Actually, I should check. Do we have any questions or anything here? Let's see. We should be good here. Okay. All right. I'm going to go back to slides. Okay. So, so how does software communicate with hardware? You've obviously, like in your previous programming courses, you can print hello world to the screen and you can read input from the keyboard. So in a way, you write software that communicates or interacts with hardware, but it's sort of done through abstractions. What I'm talking about here is how does software physically, at the very lowest level, how does the CPU talk to other entities outside itself? Well, if you think back to CSCE 212, which hopefully all of you have taken, you learned assembly language, which is the kind of the lowest level of the software stack. Did you learn any instructions in your assembly language course that are designed to perform input-output, to talk to peripherals? Well, you learned. Okay, think back, because it might have been a couple of years ago. Remember, you learned instructions that do arithmetic, logical shift, and comparison operations, right? The number crunching, that kind of stuff. You learned branch and jump instructions that cause the CPU to kind of jump around in your code and be able to perform loops and if statements and function calls. And you learned load and store instructions, which allow you to bring data in from memory into registers and vice versa. So the answer is really no. You didn't learn. There's no I/O instructions in there at all. I mean, I don't. You might have not thought of this at the time, but it's like, well, okay, how do I talk to a keyboard or a mouse if I'm writing MIPS assembly or RISC-V assembly or whichever one you learn? So it turns out at the most fundamental level, the CPU talks to peripherals through load and store instructions. In a typical system, each peripheral, or when I say peripheral, I mean hardware module outside the CPU. Most peripherals do I/O, right? They're designed for communication outside the CPU. So disk controllers, network interfaces, that kind of stuff, USP interface. Some things are not I/O. Some things are like a GPU is kind of a slave processor, accelerator, coprocessor, whatever you want to call it. But that's what I mean when I say peripheral. So each peripheral, anything that the CPU can communicate with, is associated with a range of memory addresses. And when when you load or store, when the software running on the CPU does a load or store to any of these addresses, instead of transacting data with memory, as you learned in 212, because you use a special address, you're actually conveying information between the CPU and the peripheral. So when you load, you convey information to the CPU, and when you store, you receive. So from the perspective of a peripheral, right? When the CPU loads from your address, you're giving information to the CPU, and when it stores to your address, you're receiving information from the CPU. So in other words, each peripheral owns a range of addresses. Now, of course, the memory space, the processor's main memory, is the widest range of addresses. So most addresses do go to memory, but you have these relatively small ranges of addresses compared to the memory that are owned by peripherals. These are I/O addresses, I/O ranges. And each addressable location within each of the ranges corresponds to what's called an I/O register, right? Sometimes they're called a status register or a control register. A status register is meant to be read by the CPU, and a control register is meant to be written by the CPU. So status is a way to send data out. Well, from the perspective of the CPU, the status register is what you're reading, is your input, and the control register is your output from the perspective of the CPU, right? But this is a little bit of an outdated terminology because a lot of these I/O registers can be read or written, so it's kind of a useless distinction. But the thing to keep in mind here is that when you do programmed I/O, the CPU is the only thing that can initiate transactions. So the CPU has to load or store, and then the peripheral, who's on the other end, who's the target of the load or store based on the address, has to respond. So and again, this is called programmed I/O. The CPU is the controller, the initiator, the master, basically, and so the CPU can read or write, but it's done at the CPU's discretion. So this is an example system that I've got on the slide here, and I'm showing the I/O address ranges for each of these peripherals. So I've got USB, SPI. I'm sure you know what USB is. SPI is a protocol we'll talk about a little bit later. Timer is like a real-time clock or a timer, or something that keeps track of time asynchronously with the CPU. And then a UART, you might have heard of that. UART is another protocol. It's typically used for a console, like text input and output. And if you look at the USB interface there, now notice that these peripherals are all on chip. They're all part of the same chip, but the CPU is, a part of this chip, and these are all connected through an interconnect, which is some sort of on-chip connection, way to connect these things, crossbar switch or multi-hop network, or however it's implemented on the particular chip that you're looking at. So the I/O range is shown. So for example, if you look at the USB interface, it starts at address 100 in hex and it ends at address 1FF in hex. So its range is 1FF minus 100 plus 1, which is 200 in hex, or in decimal it's 256. So if we assume that we're talking about byte addresses, which every system I've ever seen has been byte addressable, which is kind of weird because you would expect that at this point we'd be dealing with larger units of data than bytes, but every system, computer systems are still standardized on byte addressing. So this is 256 bytes. So that means the USB has a little memory space associated with its control registers of 256 bytes in this case. Now, I/O registers are often divided into bit fields. Each bit field has a specific purpose. So here's an example of one. This is an 8-bit register. Now, control registers are not always 8 bits. Again, it depends on, or I should say I/O registers rather. I/O registers are not always 8 bits. They're 8 bits. I'm showing an 8-bit example. This is because the Arduino is an 8-bit processor, or the Atmel 328P rather is an 8-bit processor that we used last spring. But control I/O registers can be wider. They can be 32 bits, for instance. But this is an 8-bit register, and it's divided into 6 fields. And some of these fields are meant to be read and some are meant to be written. and that's denoted in the third row of the table there in the upper right-hand corner. So we've got some bits and bit ranges, some fields that are write only and some that are read only. And I just made this up. This is just totally, arbitrary. So we've got a bit called halt that halts the CPU, and then we've got a flag that's called on fire. It tells you if the CPU is on fire, or the peripheral rather. Then we've got a field called temp, which allows you to read the temperature, and then we've got kind of generic ones called A, B, and C. So to access these fields, we need to be able to read and write specific bits inside of a byte or a word, more generally, right? Or when I say word, byte, I'm talking about a variable. So you're writing C code, basically. You have a variable. You need to be able to access specific bits. And this is called bit twiddling. I don't know where that term came from. But you need to be able to do this whenever you write software that talks to hardware and interacts with these I/O registers. So in this example, let's say you have a variable called val. So for now, just assume it's a variable, not a control register, or status register, I/O register. So we have a variable called val, and it's got 8 bits, and the bits are numbered from 0 to 7 from right to left. So you should be comfortable, hopefully, with that from 211 and 212. So you read these bit positions that are always read from right to left, and from 0. So we've got bit 0 up to bit 7. And let's say we want to set bit 2 to the value 1. Now, currently in val, that bit is currently 0. But I want to set it to 1, but I don't want to change any of the other bits in there. I just want to change that 1 bit. Now, how do you do that in C? We're going to be writing C in this course. That's generally the language you're using when you do low-level programming that interacts with hardware. How do we do that? Well, there's several ways. One way is you can create a temporary value, a temporary variable called temp. Set it to 1, and then you shift the value 2 bits to the left. Why 2? Because we're concerned with bit 2. We want to change bit 2. So we shift it 2 bits to the left. That will position the 1 bit inside the temporary variable into the position of bit 2. So it'll basically, we're lining it up with the bit in val that we want to change. So we've got val, that's our value that we want to bit twiddle, and we got temp, which is a little auxiliary value, temporary value that we're going to use to get there. Now you might be saying, well, oh, this is already starting to sound a lot more complicated than it should be to set 1 bit, but it turns out, yeah, there's no other way to do this. And I mean, in C, you can't. C doesn't have any native support for setting individual bits. Well, I shouldn't say that, because you could create a bit slice structure, but arguably that's probably just as much work. Anyway, so we got these val, we got temp. So if we want to set it to 1, we can take val, and then we can do a bitwise OR operation with temp, and that'll basically merge the 2 values together, sort of, and it'll set bit 2 to 1. So to do that in code, it's really just, you can just compress this all into one statement. You can say val equals val bar, a bitwise OR, and then 1 shifted left by 2 bits. Now, you might say, well, that's yeah, but you're using magic numbers in there, which is true, and obviously you can replace those with constants, which we'll do here in a bit. I'll show you how to do that. But basically, this is kind of what it would look like after the preprocessor gets done with it. So you have 1, you shift it 2 bits, you merge it in. So you might have wondered, when you took 212, why there was this huge emphasis on shifting and bitwise operations. Like, there's MIPS instructions, there's hardware instructions to do this shifts and bitwise operations, but you probably never use those in any other course you've taken. Certainly not in 145, 146, 240. You might have done this when you took robotics, 274, but I'm not sure now that they're using the Python. They've kind of raised the abstraction up a little bit in that class. So anyway, this is why. This is a reason why you need shifting and bitwise operations. Okay, well, how about setting a bit to 0? So now let's do the opposite. Let's take a value, a variable val, and let's take a bit 2. Well, once again, we'll use bit 2, but this time we want to set it to 0. So of course, I'm going to assume that the original value of that bit was 1, unlike the last example. So we're going to set bit 2 to 0. We want to force it to 0. Again, we don't want to change any other bits. So again, I'm going to use a temporary value here. I'm going to put a 1 in there, shift it 2 bits to the left. Oh, by the way, you might say, why put 1 in there and then shift it 2 bits to the left? Why not just put the value 4, which is 100? You can do that, but the advantage of shifting this way is that 2 can be a variable. It can be a parameter, right? Whereas if you put 4 in here, like a constant 4, it's it may be more difficult to make that a runtime parameter. But it's a matter of preference. Okay, so then now the difference is that if we want to set a bit to 0, we have to do something. We have to take an extra step. You have to complement, do a bitwise complement, which in C is the tilde operator, and basically flip all the bits from 0 to 1 and from 1 to 0. So that way, bit 2 is 0 and the other bits are 1. And then instead of a bitwise or, you do a bitwise and. So you take the original value val and you do a bitwise and with the temporary value, and that will basically act as a bit mask where all of the bits aside from bit 2 in the original value are just anded with 1, which just gives you whatever the original value was. But bit 2 is anded with 0, which clears it. And that was our goal, was to clear bit 0 without touching the other bit. So the code for doing this is val equals val and tilde, and then in parentheses 1 shifted left by 2. All right, so that clears a bit. Okay, so far we've talked about how to set bits, but I mentioned that with I/O registers, there's bits that you have to read, and there's bits you have to write. Well, we've talked about how to write certain bits. How about reading certain bits, reading specific bits? Well, there's different ways to do this as well. For example, if you wanted to isolate bit 3, and when I say isolate, I mean just read the value of bit 3, get it by itself in a variable independent of the other bits. So you can take the value there, and if you shift it 1 bit to the right, it'll move that bit 3 closer to the right side. In fact, bit 3 will become bit 2. And then if you shift it 2 times, 3 times, eventually what you'll end up here with is the bit 3 and the original value will become bit 0. It'll get shifted all the way to the right side. And then we'll end up with 3 zeros on the left side. And then you can do another bitwise and with the constant value of 1, and that will clear all the bits except for the least significant bit, which was the original bit 3. So the code for that in C would just be val shifted to the right by 3, and then bitwise and with the constant value 1. Now I'm showing in this case bit 3, the original value of bit 3 was a 1, but this would also work if the original value were 0. So you're going to end up with either a all zeros and a 1 or all zeros and a 0 in the output of this. So now this is assuming that we want the original bit 3 and the least significant position, like that. In other words, that this is assuming that we want to right justify. You know, we want to get it. We want to take a bit out of that field and, you know, put it in the rightmost position. But you may not. You know, why would you want to do that? Well, if you want to do any kind of arithmetic with it, basically. But if you wanted to just use this as a Boolean, like for you know, a Boolean, if you wanted a Boolean value to be true or false based on whether bit 3 were 0 or 1, then you wouldn't necessarily have to put, you know, shift it to the right. You could just basically just have a temporary variable, shift it, you know, 3 bits, or set it to 1, shift it 3 bits to the left, and then just do a bitwise and that way the original bit 3 value will then end up isolated among zeros in bit 3 of the result. So it's kind of the same thing, except, you know, it just leaves bit 3 and bit 3. And the nice thing about this is that if you were using this as a Boolean, you know, if you remember from C, in C there's no primitive Boolean type. You know, Booleans are just integers, which are considered false if the value is 0 and true on a non-zero. So if you just wanted to basically make the result, you know, either 0 or non-zero, then you wouldn't need to worry about shifting, you know, bit 3 down to the right-hand side. What's the point? You know, so this is a shorthand if you're just doing a Boolean. In other words, if you're just using this in an if statement as opposed to, you know, trying to, you know, do arithmetic. But what if we want more than one bit? Like, what if we want bits 5 down to 3, as we have with my example, the temperature, right? So in this case, we have bits 5 down to 3. Notice the notation I use, 5:3. This is Verilog style notation, similar to Python, but keep in mind that this is inclusive. So when you say 5:3, we're talking about bits 5, 4, and 3. You know, so it's including both sides of the range there. That's important to remember. So how do I isolate those guys? Well, again, I can shift 3 bits to the right. I might say, well, why 3 and not 5? Well, you want the original bit 3 to end up in bit 0, and you want the original bit 5 to end up in bit 2. So that way, the original bit 5 down to 3 should be right justified in bits 2 down to 0, and all the other bits should be zeroed out. So we'll shift it 3 bits to the right, which basically means that if you're looking at let me go back here, sorry. If you're looking at something like this in a, you know, user guide, this says 5:3. So when we do the shift, we're using the right value, right, the 3. So we're going to shift this guy by 3 bits to the right. Yes, so you can see that the yellow boxes represent the original bits that were in 5 down to 3, which was 0, 1, 1. The blue ones are the old bits 7 and 6 that are kind of garbage left over, right? Those are garbage bits. And then we got the red boxes, which are the zeros that were shifted in the left side. So, you know, it would be great if all the other bits were 0, but unfortunately they're not. We got leftover bits. You know, we got rid of the original bits 2 down to 0, but we still got the original 7 down to 6. So in order to take care of those, we're going to have to do another bitwise and so you want to AND it with 111, which is the, you know, decimal and hex value of 7. But if you want something, if you want to do it in a way that's a little bit more generalizable, you can take the value of 1, shift it 3 bits to the left, which will give you 8. You're like, well, why do we want 8? Well, then you subtract 1. So pretty much, if you want to create a bit mask in general for the least n significant bits, then you simply take 1, shift it n bits to the left, and then subtract. That's the shorthand, kind of elegant way to do that. And so then we'll end up with val 5 down to 3, right justified all by itself in its own register. Okay, so now let's talk a little bit about loading and storing to these I/O registers. How do you do that? How do you load and store in C? You guys know how to load and store in assembly language. How do you load and store in C? Well, it's basically C uses something called the dereference operator to both load and store, which is I don't know, to me is confusing because it's the same operators doing two different things. It just depends on whether the dereference happens on the left-hand side of an expression of an assignment or the right-hand side, or if you use it in like a right-hand side, meaning any expression in general. So I should have put a semicolon there. Sorry. So if you so the dereference is the asterisk, which is also confusing because that's the same operator as a multiply. I don't know why they did it that way, but basically, if you have a variable that has an address, also called a pointer in C, and you stick a star to the left-hand side, and you use it as an expression as opposed to a target of an assignment, which is what I'm calling RHS, right-hand side. That will basically cause the compiler to generate a load instruction. And if you use a dereference on the left-hand side of an assignment statement, that'll cause the compiler to generate a store instruction. Okay, so that's basically it. You take your I/O address, and now if you're doing this on an operating system, you will crash your program because the operating system is not going to let you do this. The operating system is not going to allow you to write or read to any I/O addresses. In fact, most operating systems also have virtual memory systems. So, what address the address inside your program is a virtual address. And I/O addresses are physical addresses, right? But even if you got access to the physical addresses, it still would segfault if you did this. So this only works in bare metal code. Now the problem though with this is that if you do this, you have to make sure that these load and stores are bypassing the cache, because you're assuming that these loads and stores are translating directly into communication events between the CPU and the target peripheral. And that's a bit of an issue. And the way that works is actually specific to whatever processor you're targeting. Sometimes this can be done by adding the volatile designator to your pointers, to the type of the pointer. But sometimes even that doesn't work. It depends on the compiler and it depends on the processor. Sometimes you need specific intrinsic operations. Like, for example, on some processors you would do, like, for example, you have to use I/O read and I/O write intrinsics. Intrinsics like basically look like functions, but they're just a way to translate statements directly into specific assembly language code. And so if you need an intrinsic to do a programmed I/O operation, that means that there are specific types of load and store instructions that are needed to bypass the cache and go to hardware directly. So sometimes you'll have like a load I/O and a store I/O instruction, or sometimes on other processors, like for example, the address has to have its most significant bit set to 1, which designates it as a bypassed, bypasses the cache. But this is technology specific. Unfortunately, there's no general way to teach this. This will depend on whatever processor you're using. Okay, so let's go back to our original example now, and let's work out a problem. One of the things I'm going to try to do, by the way, in these lectures is to add. I'm trying to incorporate more sample problems, the kind of problems you'll see on the exam and quizzes. So we've got our I/O register. The name of it is PNTLS. I don't remember what the heck that stood for. I made that up last spring. I don't remember what it means. And in this case, I've got some constants that are declared as pound defines. Hopefully you learned pound define in 240, I'm hoping. If this is confusing, let me know. Although it's basically just a way to define a constant that's handled by the preprocessor. So I've got a define called USB address, which is 100 in hex. This was the base address of the USB. And actually, you know what? I just realized that it's 5:07. You know what? Maybe we should stop here. I'll continue with this next time. I want to check to see if we've got any questions or let's see. Do we have any questions in the chat? I'm not seeing anything, but I might be looking at the wrong spot. Attendees. No, I think we're okay, right? Any questions? Don't see anything. Okay. Well, I'll tell you what. Yes, thank you, Robert. The programming assignments will be individual. That's a good question. Yeah, I mentioned that. Why can't I see a list of these? Why am I just getting pop-ups? Anyway, wait, oh, I see. I have to go back. Got it. Thank you. Sorry. Yes, now I've got the full list here, the chat room. Okay. Yeah, so the original version of this course was group work, but we're just going to do individual work. It's not really practical to do group work remotely. Any other questions? Okay, great. Well, this is good. I think this worked out pretty well. Got 25, so we still got less than half the class here, but I think this worked out pretty well. So I'll continue this lecture on Wednesday. We'll finish up this example, and then we'll talk about other protocols. And then we'll keep trudging away. And then next, of course, next Monday we have a cancellation. So in the spring, we usually teach Monday, Wednesday classes. So we always have that, that initial interruption at the beginning. But I think we're in good shape. Okay, well, thank you, everyone. Oh, how long are the tests? 75 minutes is the length I assign. So the quizzes we put up for, you can take them anytime throughout the whole week. And when you take them, you're given unlimited time to take them, and you get 2 attempts. But the exams have a time limit of 75 minutes, and you only get 1 attempt. And that seemed to work out pretty well in the past. No, there's no quiz this week. Well, I'll let you know if there's a quiz. I'll be sure to announce it on the announcements forum. Yes, the exams and quizzes are through Dropbox, through Moodle, and there'll probably be multiple choice. That's how we did it last semester. That's correct. The announcements will be on Dropbox. Yeah. If I was a little bit more comfortable with Blackboard, I would migrate everything there. But I like Moodle better for at this point, though. And that seems to be kind of a consensus among the students I've talked to, anyway. Any other questions? Yeah, the nice thing is anything I post on the announcements forum on Moodle will be broadcast out after 30 minutes. There's a 30-minute delay, but that doesn't matter for announcements. Now, when we do the discussions on the forums, we had some students complain about that last semester, where they said that they ask a question and a TA or I will answer it, but they won't receive the email for half an hour, which is something we can fix. That we can actually take that half an hour editing delay off. Maybe we should do that. Okay, sounds good. Well, thank you, everyone. And I will see you all on Wednesday.